just put them one level at a time.
Oh, it's okay. Yeah, right now works for me.
And then they're on to the bigger floor.
But he is an instant.
Yeah, that's.
Hello, everybody. Here we have, unfortunately, the last stock, or fortunately for you, unfortunately for us, last stock by Mark. Anyway.
Okay, thank you. Fortunately, unfortunately, I guess it really depends on you know how you've been enjoying this. But thank you for sticking around. I've had fun doing this, and hopefully you've learned some stuff. For my last lecture, I wanted to kind of switch gears a little bit and focus on kind of sort of the extension or the what word I'm looking for, but somehow there's one word that I'm looking for that is just escaping me right now, but the generalization of sort of braid theory to surfaces in four manifolds. So if you study knot theory, one of the things you come across quite early is sort of braids and how every link can be represented as a closure of a braid. And somehow this gives you some structure where you can all of a sudden bring in some algebra. It also just allows you to sort of have a bit more rigid geometric structure, which you can make use of in various applications and things like that. So somehow this braiding aspect ends up being really important in 3 dimensions. And the question is, does sort of similar ideas and similar structure, can you, first of all, define it in 4 dimensions? And if you can, what does it give you? So I'm going to kind of introduce sort of like develop the theory of sort of braids, surface braids in 4 dimensions, kind of parallel to what you've probably seen in the classical case. And so you haven't seen this before. How many of you have seen like surface braids or braided surfaces? Okay, a couple, a few. Okay. So the question is, well, how do you generalize the notion? What is the correct way to generalize the notion of braiding to, braiding strings, like we braid our hair, to like surfaces, okay? So here's sort of a classical braid, and we sort of have to, there's lots of ways to view a braid, a classical braid. You sort of have to pick the right viewpoint in order to like sort of generalize it naturally. So the viewpoint that I'm going to take is that a braid is actually a submanifold of a solid filled-in cylinder. Okay, so essentially this is just a disk cross an interval. Okay, and a braid is a submanifold of this, a properly embedded one-dimensional submanifold, but it has the property that it sort of travels in a monotone direction. Like it always is sort of traveling from left to right. It doesn't ever double back on itself and go right to left. It's always sort of traveling in one direction, even though it might sort of twist around itself. So we want to sort of capture the idea that it sort of is always traveling in one dimension. And there's probably a few ways you could do that. You could parameterize it and say that you want, some derivative to be positive or something like that. But sort of I think the nicest topological way you can kind of do that is you can look at the projection from B2 cross the interval. You can project down to the interval, right? So this is just a product space. And so we can just take the natural projection to one of the factors. And what we want is I don't know, can anyone phrase the property of being a braid in terms of this projection map? Anyone have a guess as to what that property is? Yeah. We will get to branch covers in a second. This is going to be, Is
it just an injectivity on each strand?
It will be injective on each strand. There's a few ways to say it. Branch cover in this dimension would be just a regular covering space. So you could also talk about sort of injectivity, or you want it to be like a local homeomorphism or something like that. And it turns, probably one way you can phrase it, maybe there's a few ways you can do it, is you can essentially just say that you want that to be the restriction of the projection to the braid to be a covering map. So maybe I'll just say it like this. So a classical braid theta is a submanifold. Let's say, is a codimension 1 submanifold of B2 cross this interval. Oh, codimension 2, yes. Codimension 2 submanifold such that the restriction, so pi 2 is just going to be my projection to the second factor. The restriction of this to beta is a covering map. Okay. Now this is definitely probably not the way you learned about braids the first time you saw braids, but this is sort of a nice topological characterization of what a braid in a solid cylinder looks like. Okay. So any questions or comments there? So yeah.
Do we fix the boundary?
Yeah, so typically when we want to talk about like equivalence classes of braids, we're gonna think about it, we're gonna think about isotopy rel boundary. Yeah. Yeah, that's a good point to bring up. So what's the generalization here then? If we want to instead get a surface instead of a bunch of arcs, what do we change here maybe? Anyone want to take a stab at it?
Replace the interval with a two-dimensional disk.
Yeah, so we're gonna keep it a codimension 2 submanifold, but we're gonna increase the dimension of the ambient space. So instead of ending up with a bunch of arcs, we're gonna end up with a surface. So we'll sort of generalize this by, I'll use a different color here. Okay, so we'll say a surface braid beta is a codimension 2 submanifold of a disk cross a disk, so that the restriction of this projection map is a covering. Okay, so that seems like that's how we generalize it. That's a nice way to do it. Does anyone see a problem with this approach at generalizing?
Are you worried about it being connected,
The
surface?
I don't really care if it's connected. But somehow, yeah, so I'm not so concerned about the braid itself being connected because like in the classical case, our braids are usually not connected. But there's kind of another problem. Oh, to be like,
That's trivial braid.
well, yeah, so we'll actually talk about that. Eventually, we'll kind of talk about wanting the boundary to be a trivial closed braid. This is sort of another fishing expedition where I'm looking for you to say what I want you to say, and so I'll kind of, I mean, there's maybe a few problems if you're trying to come up with an interesting theory, but maybe if you think about it for a few minutes, or if you sort of apply, your covering space theory. What kind of covering spaces are we going to get of a simply connected space? So I have, so the picture is, I have D2 cross D2, like this, and I'm trying to project down to the second D2 factor, and I want that projection to be a covering space. Well, so let's stay with covering for a second. Because this is simply connected, because the base that we're projecting to is simply connected. Yeah, you can show, I guess I'm using B's and D's interchangeably here. Okay, yeah, because the base of this projection is simply connected, really the only covering spaces we're going to get are just going to be like trivial coverings. Okay, so I mean, after isotopy, you can kind of make them look just like a bunch of disks that sort of sit above B2 like a stack of pancakes, right? So that's not super interesting.
Well, that was true in dimension 2.
Yeah.
Yes, well, you're right. So you're right. They are, but yeah, I guess you're right. I mean, but if you allow some like. You're right.
There is linking here, there is no linking there.
Yeah, there's no way for it to link. If you pick something that's like, if you pick a surface braid or a braided surface and you require sort of isotopies to be rel boundary, then I mean you will get some. You won't get any sort of interesting braiding along the boundary. So yeah, I mean you're right, this is not maybe a good argument for why it doesn't work, but yeah, so the way that we're actually gonna generalize this, we're gonna add the word branch covering, okay? So I'll do that in red here. Okay, and how many of you know what a branch covering is? Okay, so most people do, not everyone maybe, but so let me just define what a branch covering is. Oh, I think I have some pictures here that I skipped. Okay, all right, so yeah, what is a branch covering? I'm just going to consider branch coverings of surfaces. So I'll say a smooth map say between some surface F and some surface G is a branch covering. If every point in the domain has a neighborhood on which P looks like, I mean, there's lots of ways to define branch coverings. Probably just in the case of surfaces, it's a smooth map where you can pick coordinate neighborhoods around every point in the domain, which make it look like Z gets mapped to ZK for some K in the interval 1, 2, 3, or not the interval, but the set 1, 2, 3. So for some natural number bigger than 1. Yeah.
Maybe you said this and I just missed it. Why is the natural thing to do D2 cross D2 instead of like B3 cross?
Oh,
like I'm thinking of a movie, right?
Yeah, so why not turn it into B3 and then still project down to the interval? I've not thought about that. You would get, I'd have to think about that. Why that's not natural to do and what you get out of that.
Yeah.
You get a bunch of, braids that sort of move along.
Yeah, how loop break groups and other motion groups are done.
Those are loop braid groups?
Yeah.
Okay. Something I'm not, so it sounds like people do that, but it's just given it's called loop braid groups.
So if there's circles that are braided.
Okay. Other questions or comments? So a branch covering, every point in the domain of a branch covering is either going to look like a local diffeomorphism like this, or you could have sort of this picture, which we saw with sort of broken surface diagrams, which looks like sort of Z gets mapped to Z squared, or you could have sort of even higher order branch points where you get things like Z gets mapped to Z cubed, etc. And so these sort of, if you sort of are trying to arrange it in a covering space picture, you sort of, these branch points sort of look like these parking structures where you can kind of go from one level to the next by sort of completing a full loop around one of these branch points here, okay? So let's see. There's actually lots of ways to sort of just define branch covers. A lot of times you define a branch cover just to be a smooth map where sort of away from some codimension 2 subspace, it's a covering map, and then you get some sort of conditions about what it looks like near this codimension 2 set. But so sort of around any point in a branch cover, if you pick a regular value in the base and you look at sort of the preimage of a neighborhood, it's either going to look like some little disk neighborhood. It's going to look like a stack of disks, or if you pick a critical value and look at the preimage of a neighborhood of that critical value, it may look like what you have on the left, where you have some points in the preimage that have sort of higher order branching around it. Okay. So any questions there? Comments? No? Okay. Should do a thumbs up, thumbs down, like Aru says. Okay, thumbs up, generally speaking. Okay, so this lets us sort of define the idea of a braided surface. A surface braid beta, well, need to be a little bit careful here. So I'm going to change just the way that I've phrased it to a braided surface. A braided surface beta is a codimension 2 submanifold of B2 cross B2 so that the restriction of the projection map is a branched covering map, okay? And so what does a picture of such a thing look like? Well, we've got this surface embedded in B2 cross B2. It's a branch covering, so it has some branch points where locally we have this branching picture going on, and it's getting mapped down to B2. So if you look at the boundary of this thing is always going to be a closed braid that lives inside of this this torus that lives inside the boundary of B2 cross B2. So the boundary of a braided surface is a one-dimensional closed braid. And a lot of times we might want so I'll say this. So if the boundary of our braided surface, and I guess in the picture I called it W, so I'll call this W. If the boundary of our braided surface is a closed trivial braid, okay, then typically people call that a surface braid. Okay, so the nomenclature is a little bit like is a little bit subtle. Like if you hear someone say like a surface braid, usually they're talking about one where the boundary, you've got this torus that lives in the boundary of D2 cross D2, and they want sort of the boundary of the surface just to like be trivial. Around the wrong way. Okay. So if you have a trivial boundary braid, then you call the surface a surface braid. Otherwise, it can be called a braided surface. So braided surface is a little bit more general. A surface braid is a special case. So really tight note, yeah.
Yeah, so when you're drawing this like C maps to C squared branch covering of the disk, it looks like there's an honest intersection point on the boundary. So where is this like overcrossing information?
Yeah, so this comes from this is kind of the same as that Whitney umbrella that we saw, where when you're taking a broken surface diagram, you're projecting down to 3 dimensions, and in 3 dimensions, you're sort of forcing yourself to have an intersection point. But inside the 4-dimensional space, you don't have an intersection point, and so inside the 4-dimensional, so if we look at it like a, okay, so if we look at like sort of, you know, what happens when you take the surface, you project down to 3 dimensions. We would have to do a broken surface diagram to sort of determine which way that crossing will go 1 dimension up, because we could have this situation, or we could have the crossing going either way. And so there's a sign attached to each branch point, either a positive or negative branch point, and the sign of the branch point will tell you whether you get sort of the positive or negative crossing in the boundary. But yeah, in these pictures here, when we're projecting down, we kind of lose the ability to distinguish that, at least if we're drawing a whole boundary. Other questions? Yeah.
Why is that second one such a natural thing to consider that we call it a surface braid and allow it to keep that name after, you know, defining braided surfaces?
Because we want to, essentially we want to like do things like Alexander's theorem, where we take closures of surface braids to get surface knots or knotted surfaces. And so yeah, so like this is kind of the thing you want to look at if you want to like generalize Alexander's theorem and Markov's theorem in higher dimensions, yeah. But these braided surfaces also come up in a lot of like constructions and are useful in their own right, but maybe they should have a different name. So
Do you see either used more in the literature? It's either more popular. than
Oh,
the other?
I don't know. Yeah, I mean, it kind of depends on, I kind of see, I don't know, I wouldn't want to speculate, like stuff that I think about, I would tend to think about these things more. But other people kind of, are interested in other, in other applications would see surface braids maybe used more. Yeah, Jessica.
So you want to define then a group structure, you need it to be, or are you going to talk?
I won't talk about the
Can you
group
repeat the
structure.
question?
It's about if you want to define a group structure, then do you need it to be a surface braid, or can you do it for any braid? Like,
So you can just define a multiplication by sort of taking two surface braids and sort of sitting them right next to each other and sort of gluing a segment along their boundary. It doesn't give you a group structure
okay,
because there are no inverses. But I guess, yeah, but you get sort of a multiplication in that way. You could define it here, although you'd have to sort of pick a segment. You sort of have to glue along two segments that match. So maybe you take a little trivial segment, and I don't know about well-definedness there. You definitely can define you have a well-defined operation here. And you might be able to make something well-defined here, but I've never
is
thought.
it useful to consider such an operation, or is it?
I mean, it's there. I'm sure some people think about it, but it's, yeah. It doesn't give you a group. So you do lose that sort of that algebraic structure you have in the classical situation. So, yeah.
Is it possible to get inverses by modding out by the right equivalence relation, like accordance or something?
Yeah, I suppose, so if you allowed branch points to cancel in pairs, like you could come up with a group operation. So yeah, so you could mod out by some canceling branch points in pairs. And so if you had like the correct branch points on the correct levels, and you could sort of define a cancellation operation, which may allow you to get an inverse and therefore a group. So it's a good question. Okay, other questions or comments? Okay. So okay, so maybe I'll just make two comments. Because we're projecting down to an oriented space, we can always lift an orientation up to the braided surface. And so braided surfaces are always going to be orientable. Okay, the orientation just comes from the orientation of the disk. And although it's like quite natural to sort of think about branch coverings that have higher order branch points, in sort of the smooth world, you can always perturb, like say you have sort of a degree 3 branch point like that, you can always sort of perturb the embedding a little bit to sort of split up the branch points into some number of these degree 2 branch points. So oftentimes people will sort of think about simple surface braids where you only have local branching of degree 2. You don't have those higher order branch points, okay? Because you can always kind of wiggle the situation so that these higher order branch points kind of dissolve into degree 2 branch points. So basically everything I say from here on, we'll kind of assume that we're working with what's called a simple surface braid, so that we only sort of have two sheets that come together and interact. Okay. So I promise that this is sort of a generalization of the relationship between surface braids and knotted surfaces is kind of analogous to the relationship between classical braids and links. And so to sort of see there is sort of an analog to taking braid closures. So here I am thinking about surface braid. So I want the boundary of my braided surface to be trivial. And if that's the case, then I can think about just sort of capping off each of these boundary components with a disk. Okay. And it takes this surface and it turns to this surface with boundary and it turns it into a closed compact surface. So this is sort of our closure operation. And this is kind of where, if you want to think about sort of like Kamada or like Markov's theorem and Alexander's theorem, you definitely need to be working with a surface braid and not a braided surface whose boundary could be weird. Okay. So let me state the sort of the relevant theorem. Okay. So this is a theorem due to I think due to Vero sort of originally, but the first sort of proof you can track down is due to Kamada. So all right. And this theorem says that any closed orientable surface say probably, yeah, closed orientable surface in S4 can be expressed as isotopic to closure of a surface braid. Okay. So hopefully you can kind of see that this is the direct analog of like Alexander's theorem in the classical dimension. And this is, in fact, not super hard to prove with, like, say, banded unlinked diagrams. So we'll kind of go through the proof here of what this looks like using, say, banded unlinked diagrams. But in order to do that, we want to know, we need to sort of understand what one of these surfaces looks like as a banded unlinked diagram. And I should be a little bit careful because these are not going to be, if I'm talking about sort of if I'm talking about a braided surface or a surface braid, then it's strictly speaking not a banded unlinked diagram because I'm not sort of assuming that it's all closed off as an unlink, but we're going to sort of use bands to describe what the branch points look like. So here's kind of a movie of the two types of branch points we might see in our braided surface or surface braid. So we sort of just see two nearby strings that come together. They interact for an instant, and they, you know, with a saddle point, they give us a crossing, whether it's a positive crossing or negative crossing. And so as a banded unlinked diagram, or at least in terms of a band, how would I express this saddle point here? How many bands would I need? One. And what's, oh yeah. Yeah, so we can sort of express this saddle point here with a single band, but that band is going to have a half twist. Okay, just a single half twist. Okay. So depending on the direction that we've twisted that band, we're going to get either a positive crossing or a negative crossing. Okay. So this is sort of the local picture of a branch point. And so if we build up an entire surface using this, then up top we have a braided surface. So if you sort of look what, you know, you look at, you can kind of figure out what the boundary braid looks like. So if you want to sort of see what the boundary braid looks like, you can sort of just express the braid. And I'm not going to copy this one down, but you can sort of like, well, it'll sit like this. Say you have something like this, and you have bands here and here, okay? Well, what the surface braid is going to look like is it's going to be the braid closure you get by sort of, first of all, ignoring the bands and just looking at this braid. And then you can sort of think about this traveling around the front side of the braid, and then sort of traveling on this edge around the front side of the braid. And then to fill in the front part of the braid, you take a copy of this, but where the band surgeries have been done, and that's going to give you sort of the front part of the braid, okay? So you're going to sort of see two copies of this braid in the boundary of sort of from the banded unlinked diagram, where sort of on one half, the bottom half of the boundary, you haven't done the band surgeries, and then on the top half, you have done the band surgeries. So you can kind of see what the boundary surface braid is going to look like. And if you look at the first one there, you can kind of see that that's not going to give you a trivial braid closure. So that's not actually a surface braid. But I kind of modified it down here so that so this indeed is a surface braid. And when you close it off, this is what the banded unlinked diagram would look like. So any questions about like how this is sort of that picture that represents that closure operation? We sort of have just closed off each of the endpoints here with an arc. And when you sort of fill that into a broken surf or to a banded unlinked diagram, that gives you that picture where you sort of filled it in with discs. Any questions? Yeah.
Is this only gonna, so we need to have unlinks when we close up the braid here, or?
Yeah, so like the picture here. You want the boundary just to be composed of an unlink so that those discs can fill it in, yeah.
If I have like a non-trivial braid, then I'm not gonna be.
Yeah, you're not gonna be able to close it off in this way, yeah, yeah. Without sort of maybe adding new branch points, but yeah. If you want to fill it in with discs, you definitely have to have unlink on the boundary.
Okay.
Okay, so any other questions on this picture here? So anyone wanna take a shot at how to prove this? So if we wanna take an arbitrary surface and we wanna put it into sort of braided position. Anyone have a guess as to how to start this operation or this? So essentially we want to go from an arbitrary banded unlinked diagram to something like this. So we want to basically clean it up, okay? And basically braid everything. So where might a good place to start be?
Braid the,
What's that? Oh, so sorry?
braid the original link without ignoring it.
Braid the original link while ignoring the bands. That might work. But the way that I've seen this done and the way that, yeah, I don't know that wouldn't work. You might be able to get that to work. For me, if I look at sort of this picture here, the bands are positioned really nicely, right? And the essentially all the heavy lifting of the braiding is being done by the link. So the way that I would probably approach this is I'd first of all take the bands that I have, shrink them down to be really short, and give them each a half twist. Okay. And I'm going to give them a half twist, and then sort of, I may have to do a little bit of rotating, but I want them to I want to pick a braid axis so that these bands look like little crossings. So for example, if this is the axis of my braid, something like this, I want my bands to sort of give me crossings with respect to this braiding direction. So a band like this would be good because sort of both before and after the surgery, it's going to look like it's going to be traveling in the correct direction. I probably wouldn't want to have a band that looks like this, right? Because before, after the surgery, it's going to be braided, but before the surgery, notice it's not going to look braided. So I want to kind of give my bands all a half twist and then sort of position them so that they sort of line up with the braid axis in such a way that both before and after the surgery, they're going to be traveling in the correct braided direction. Does that make sense? I don't want to make it super precise, but yeah.
Where did I see the axis in the previous?
Where's the axis here?
Maybe in the previous example.
Yeah, so the axis I think is going to be like right here.
I mean, in the.
Oh, in the
previous examples.
I see. In the previous examples. So here the braid axis would be like right here. And so like before surgery, we're sort of always traveling counterclockwise around, or clockwise, I guess, the way I'm doing it. After surgery, we're still sort of traveling counterclockwise around, or clockwise around, sorry, mix those up. So it's, yeah, you position the band so that both before and after surgery, you're gonna be traveling in the correct direction around the braid clockwise.
When you say clockwise, are you slicing the braid by some?
By slicing the braid.
When you say clockwise, it implies it's something one-dimensional. So, but the object is two-dimensional. So
So I'm essentially treating it as a one-dimensional object right now. So I'm doing everything in that middle cross-section of the banded unlinked diagram. And so I'm essentially gonna try to apply like the one-dimensional Alexander's theorem to a link, but just I've got these bands that are in place, and so if I position the bands sort of correctly, then I can braid everything else, and that braids that middle cross section, but I've still got sort of the top and bottom part that I'll have to deal with in a second. So like this is what I'm trying to get to here. is I'm gonna position my bands, and then I'm essentially gonna keep the location of my bands fixed, and then use the proof of Alexander's theorem in the classical case to sort of braid everything around an axis that I've selected. Does the endpoint make that middle step a little bit more clear what we're trying to do? Does it? Okay. Any other questions? No? Okay. So once we position these saddle points, we can essentially braid the link. And if you go through sort of the original Alexander's theorem and you look at sort of, there's a few different proofs of it, you can sort of convince yourself that this can be done. Essentially, you look at where the axis is, and any parts of the link that are traveling in the wrong direction, you sort of just stretch them over around the axis so that now they're traveling the correct direction. Okay. And there's algorithms that you can find to sort of identify those strands and stuff. So once we're in this situation, you might think, hey, we're done. We've essentially expressed our banded unlinked diagram in a way that makes it look like a braided surface. Are we truly done though?
Is that an unlink?
Probably not. What's that?
Do you know if that's an unlink?
I actually don't know if this is an unlink. I did this part really carefully, and then I was like, I can't like braid. I was running out of time. So I
don't mean like that drawing, but like, do you know that you get an unlink?
So if the original diagram was a closed surface, then this, both before and after surgery, this should be an unlink. And again, like, this picture I just made up, but
it's not just a trivial braid.
Yes, that's the problem, is that this thing will be an unlink, but it won't necessarily be the closure of a trivial braid. Okay. And if you really want to braid the entire picture, if you really want to braid the entire two-dimensional closed surface, you have to sort of make sure that you can cap it off with a bunch of maximal discs that are all sort of nice parallel embedded discs, right? If this thing here is not a closure of a trivial braid, then yes, there are some discs that you can cap it off with, but those discs might have to get twisted up and be really unbraided, okay? So the trick then is because this is an unlink and it's not, it might not be the closure of a trivial braid, but it is an unlink, that there's a sequence of Markov moves, so stabilizations and isotopy through closed braids and destabilizations that allow you to go from this complicated closed braid picture of the unlink to a trivial braid closure of the unlink, okay? And so we know that there's sort of a sequence of sort of stabilizations and destabilizations and braid isotopies that allow you to simplify this picture to a picture that looks like this, okay? So maybe we've got some ugly braid here, which may have more strands or less strands, who knows? And we know that there are some braid isotopies, stabilizations and destabilizations by Markov's theorems that allow you to go from here to here, okay? So the way you then use this is, a stabilization looks like this. If you realize this stabilization or destabilization as a banded unlink, a stabilization just consists of adding a minimal disk and a canceling band, whereas a destabilization is basically just running this picture in reverse. Essentially, you can sort of take the sequence of moves that Markov's theorem gives you and express each of the stabilizations and destabilizations as either like a minimal disk plus a saddle point or a saddle point plus a maximal disk, depending on which direction you're going. So that gives you a bunch of new minimal points, maximal points, and saddle points. And what you can then do is you can push all the new minimal points down to the bottom, all the new maximal points up to the top, and all the saddles to kind of the middle level. And that's gonna then, it's gonna change you're going to change the diagram you get, because now you're going to have more saddle points. You'll have sort of new components that were created from minimal points and stuff like that. But you can, in that way, you can sort of complete the construction so the entire surface is now braided as opposed to just the middle section. Okay. So there's kind of this last little step where you have to do some rearranging. You braid the middle section, but then you have to do some rearranging to sort of make the whole thing braided. Okay. Questions there? Yeah.
Where did we use the orientability condition?
Where did we use orientability? So when you are originally positioning the bands, if any of the bands are non-orientable, then you're not going to be able to position them in a way so that they sort of, you're traveling in the correct direction both before the surgery and after the surgery. Like if you have a non-orientable band, then you can add the half twist, right? You can add a half twist like this. So this is going to be something like this. And so before the surgery, you're not oriented in this picture here. After the surgery, you are, well, I mean, it doesn't make sense to say whether you're oriented or not because there's no orientation. So it essentially comes down to the point when you're arranging the bands, you can't arrange the bands correctly. Yeah. Okay, so this gives you the Alexander's, basically the analog of Alexander's theorem. You can also there's an analog to Markov's theorem due to Kamada. And I think I have the statement on the board. Oh yeah, so what is the sort of the analog to a stabilization? So the classical Markov's theorem tells you that, if two braid closures give you the same or give you isotopic links, then they have to be related by a sequence of stabilizations, destabilizations, and isotopy through closed braids. The four-dimensional Markov theorem is essentially the same thing. And its proof is due to Kamada. And so if the closure of W and W prime are isotopic surfaces, then W and W prime can be linked through braid isotopies or stabilizations, destabilizations, and isotopies through surface braids. So the statement is essentially the same as the classical statement on the nose. The only difference is we need to sort of make sense of what a stabilization or destabilization looks like in the closed surface braid situation. And in this situation, what is a stabilization? Well, to do a stabilization, you take your surface braid closure, you add a sphere in the middle, and then you add sort of two canceling branch points that connect that new sphere component to the surface braid closure you started with. And if you want, a good exercise would be, why is this banded unlinked diagram give you the same surface as that banded unlinked diagram? So we know that if these truly do give you isotopic surfaces, then there should be some sequence of isotopies, band slides, and band swims that allow you to go from here to here. So that's maybe an exercise to work on if you have some extra time. Okay, so any questions before we move into the last part, which is just like surface braid charts and no? Okay. So the last thing I want to talk about is I mean, the whole theme of this mini course is kind of like ways to represent surfaces in kind of a diagrammatic fashion. And so by using sort of like surface braids and surface braid closures, we'd like to sort of come up with a way to sort of come up with a different way, an alternate way to represent a knotted surface. And we can do that using braid charts, okay? So here I've got a kind of a movie description, a motion picture description of a braided surface. And I've drawn these vertically, okay? So I'm gonna kind of just like highlight sort of where the action's happening. So from sort of the first still to the second still, I've just done an isotopy where I've pulled one strand over another. From the second to third still, notice I'm sort of pushing, second to third still, I've taken the third strand and stretched it over the second strand. And then moving on, I'm gonna, from here to here, what have I done? Yeah, I've had a band or a saddle point or a branch point of my surface braid. Over here, I'm going to do a Reidemeister 3 move or apply a braid relation, and I'm going to pull this second strand, or at least that first strand over there over that crossing. And then I'm going to have 2 branch points, which eliminate those 2 highlighted crossings here. So I get 2 branch points in between here. And then I get these 2 crossings that can cancel, okay? So this gives me sort of a braided surface that I can describe. It gives me a surface braid, in fact, because I'm starting and ending with trivial braids. But I'd like to sort of represent this in one picture without having to sort of redraw a sequence of braids. So kind of like banded unlinked diagrams, we want to take like a whole interval worth of information and sort of condense it down to a single picture. So the way that I do this is I use what's called a braid chart, and probably the easiest way to describe this would be just through a picture, an example. So notice what happens is I pull that first strand over the second strand, and in doing so, I create 2 canceling copies, okay? Or 2 canceling crossings, I should say. So I'm going to think of sort of each braid as corresponding to a slice of this diagram. And if I take a slice of this black diagram here, I get a strand that's labeled with a 1, and on one part it's sort of passing in this direction through my slice, the other part it's passing through this direction. So I interpret the fact that this cross section here has 2 intersections as telling me that my braid has 2 crossings. One is a positive sigma 1 and one is a sigma inverse. Does that make sense, kind of? I think if I draw more, it'll be helpful. So then as I go through this braid, I'm pulling that third strand over the second strand. And so that creates a new segment here. And so if I take a cross section here, now I've got sort of my sigma inverse, my sigma 1, sigma 1 inverse, sigma 1. This is a sigma 2 and a sigma 2 inverse. And then from here to here, I'm adding a branch point, or I'm passing a branch point. So that now creates a new arc in my braid chart, okay? And because it's a branch point that creates a crossing between the first 2 strands, I label it with a 1. And yeah, so the question on how this is like what I'm doing here, like, I don't know. I thought the best way to describe this without going into too many words would be with a picture, but now I'm realizing maybe some words would have been helpful.
There's a branch point between 4 and 5 as well.
Between 4 and 5, yes, right here, because it's that crossing second from the bottom that disappears. Yeah. So essentially, these black dots correspond to branch points, and so they correspond to either the birth or death of a crossing. Whenever you see sort of a local extrema like this, that corresponds to 2 crossings getting sort of 2 canceling crossings being created, and they sort of will just, continue on through the braid until something happens to them. Here, I'm doing a Reidemeister 3 move, so I have an interaction between.
Where did that second point come from?
Oh, where did this second point come from? It came from the fact that, I didn't highlight this. There should be, and I guess this is not right, but there should be a red dot, I think, around that crossing there. Because it disappears.
Wait, is it not the 3 things that are over there?
No, that's
crossing.
Yeah, so I sort of, between this diagram and this diagram, I got rid of that crossing there. And then I brought sort of the 3 crossings closer together in the next diagram, because they're going to interact as like a Reidemeister 3.
Oh, cool. Okay.
3 crossings.
The
one that you just created.
Yeah. Actually, you know what? I brought this in my carry-on, and I haven't used it. Instead of trying to jump, I was like, can I jump or something? Okay. So this crossing here disappears. And then this crossing this crossing, and this crossing sort of get brought closer together because they're going to have a Reidemeister 3 applied. And so when that Reidemeister 3 is applied, all three of these crossings, which correspond to this point here, this point here, and this point here, they're going to come together and they're going to interact. Okay, and so this white vertex here sort of denotes that there's been a Reidemeister 3 move applied. And then I have sort of, notice from here to here, I have a branch point and this crossing disappears. From here to here, I have another branch point and this crossing disappears. So how do I represent the fact that those crossings disappear? Yeah, I get black vertices, those correspond to branch points. And then these two crossings are sort of canceling crossings. So what's going to happen to this endpoint and this endpoint? Yeah, they're going to join together, okay? So this is what's called a braid chart. It gives you a way to sort of represent or it gives you a way to represent a braided surface or a surface braid if you'd like. If you had started with non-trivial braids at the left and right part, you would just end up, you would have a diagram where you start with arcs instead of an empty diagram on both endpoints, okay? So you can use this to describe braided yeah.
The black stuff continues with the blue stuff above.
Yes, yeah. Yeah, so so from this picture you can reconstruct the sequence of blue braids. And in fact, there's one type of move that I didn't include. So you could have, because I only used 3-stranded braids, I couldn't illustrate this, but if you have crossings that are sort of between sort of non-interacting strands like this, of course, in the braid group, you can sort of switch the order of these crossings using that far commutativity. And so in a braid chart, this would correspond to sort of just a crossing between an I and a J strand, provided that I and J are at least 2 apart, okay? So questions there? I think I'm actually, yeah.
Could you explain again where the arrows are coming from?
So if you notice here, where I created a pair of canceling crossings, notice I like pulled the left strand over the right strand. So I have a negative, like I have a sigma 1 inverse here and a sigma 1 here. The arrows are just sort of telling you that if this strand is oriented like this, the orientation sort of tells you like whether it's a positive crossing in the braid upstairs or a negative crossing. So I guess the convention I've chosen is that if I'm moving from left to right, then the corresponding crossing is a negative crossing, and otherwise it's a positive crossing. So it just determines the signs of the crossings. I think there's another hand. Yeah.
Small comment.
Yeah.
In usual notation, orientation is reverse.
Yeah, I probably may have picked the reverse orientation. Yeah. Yeah. So so check carefully sort of the convention that's being used. I guess Kamada's convention is going backwards, or
yes.
Okay. Other questions or comments? Okay. So the question is as well, if I get a diagram like this, I want to sort of understand, up to what set of moves is this thing invariant, or is the resulting surface braid invariant? And there's a set of braid chart moves that Kamada gives. Okay? So Kamada's theorem, maybe I'll just write the theorem on the board, then I'll show you these chart moves. So theorem, this is due to Kamada. Okay, so 2 braid charts, gamma prime, determine equivalent surface braids if and only if they can be related by chart moves. Okay, and because I'm essentially out of time here, essentially what these chart moves are going to be is you're going to look for a disk E, okay, where outside of this disk, the 2 charts are the same. Okay, so you might have some stuff going on like this, some black vertices, etc. And outside of E, we're assuming that gamma and gamma prime look the same, but inside of E, they could be different. And so we want to describe sort of like the corresponding Reidemeister type move that we can use to change this diagram. So the first thing is that if inside of this disk, neither of gamma nor gamma prime have a black vertex, meaning there's no branch point, then you can essentially replace what's inside this disk with anything else inside the disk, as long as it sort of matches up correctly on the boundary. So as long as there's no black vertices in here, you can essentially replace anything with anything else, as long as it sort of correctly aligns with what's on the boundary, okay? So that's the first move, and essentially what that corresponds to is, you've got your braid. You can sort of mess whatever you want around, and in terms of the braid chart, that's going to give you sort of a localized picture, but you just can't add branch points or remove branch points, okay? The other two types of moves are you can sort of pull, if you have sort of I and J intersecting like this, where I and J are far enough apart, you can just pull a branch point through and it doesn't change anything. And the third thing is that if you do have one of these Reidemeister 3 situations and you have a branch point like this, you can essentially pull it out, okay? So I want to prove that essentially, braid equivalence can sort of be translated into these braid chart moves. And two charts determine equivalent surface braids if and only if they can be related by these moves here. So I am out of time, so I'll stop there. Any questions? Yeah.
Equivalent surface braids are isotopic surfaces?
Yeah, so yeah, so if you have equivalent surface braids, their closures will be isotopic surfaces, yeah. Okay. So equivalence of surface braids is essentially isotopy through through surface braids, which is rel boundary. So the boundary is fixed during those isotopies. I need to be careful because you raised your hand and I have the clicker. I have the laser and I almost lasered you, so. If you have a question, just close your eyes, raise your hand, wait till I call on you, so. Yeah.
So I guess if we have a knotty surface and a surface braid, we can do the satellite operation. We can do a satellite operation? Yeah.
Yes, there are ways to do satellite operations for surfaces. And are you saying for braided surfaces, like do a satellite operation?
If I have a surface braid, that will be my satellite pattern.
Yeah. So you could do exactly like this type thing. Take a surface braid closure, and then pick a 2-knot. Take its tubular neighborhood, and then embed your braided surface along that. Yeah, that's definitely something you can do. Yeah. Other questions or yeah?
So, I mean, you stated theorem for closed surfaces that everything's a braid, but so for surfaces in the 4-ball boundary,
yeah,
put the knot in a braid. There's also a theorem, right?
Yeah. So there's this, and I should have had this picture right. So Rudolph has a theorem that says that yeah, maybe I'll just draw the picture quickly. So Rudolph has this nice theorem that says, if you start off with your 4-ball and you have some knot that bounds a ribbon surface, doesn't have to be a ribbon disc, but could be a higher genus ribbon surface, inside the 4-ball, you can essentially, like Dave is suggesting, you can sort of arrange the boundary, you can sort of apply this braiding to the boundary, and as you're braiding the boundary, you can also arrange that the ribbon surface inside of it looks like a braided surface. So essentially, as long as you're starting with a ribbon surface, it can be braided. It can be turned into a braided surface. I think I said that correctly.
You sort of already answered my second question. I was going to ask if you can detect whether it's ribbon or not, but I mean, you're saying if it's braided, it's automatically ribbon.
Yeah. So if you maybe the best way to see that is just to go back to this picture. So essentially, yeah. So maybe this is a better picture than what I drew on the board. But if you start off with a ribbon surface in the 4-ball, you can always, by Rudolph's algorithm, you can always put it in this position, and sort of explicitly, this has to be a ribbon surface. You can sort of pick your height function and see that it has to be a ribbon surface. So there's things you can do with non-ribbon surfaces, but you end up getting these like maximal, you just can't get rid of the maximal points, so.
Wait, this is different from like Rudolph's construction of like slice surfaces for say quasi-positive braids, right? Because he doesn't have any of these branch points.
So I think in his like, I think in that paper, he is like, he's using these things, like he's proving that like quasi-positive, are you talking about the quasi-positivity is equivalent to being like the.
Realizes the slice genus, yeah.
Oh, yeah. So he uses braided surfaces there, because I think he represents it as, he proves it for quasi-positive things. And then he's able to like add in bands and show that by proving it for quasi-positive, the slice Bennigan.
What I'm confused about is like all those surfaces are like you can project them into S3 and get like ribbon surfaces in the 4-ball. So there isn't going to be any, like there aren't any of these like funky branch points that are happening.
You get ribbon surfaces in the 4. No, so his picture takes explicitly a ribbon surface, and you take the bands and you give them all half twists, and so you're sort of constructing. You're sort of position. The braiding that he does is all inside the 3-sphere. Like he pushes his ribbon surface into the 3-sphere and then does this braiding in such a way that it can then sort of push the interior back into the 4-ball. And in the 3-sphere, yes, there's these ribbon intersections, and when you push it back into the 4-ball, you get rid of the ribbon intersections. But because of these little crossings that he has, there's going to be branch points inside the 4-ball. So I can bring up the picture that Rudolph draws and like show you sort of where the branch points show up. Yeah. Yeah.
Could you repeat the definition of equivalent?
Oh, equivalence. Yeah. So equivalence is say W and W prime are equivalent if they're isotopic through, I should say ambiently isotopic through through surface braids. And I want the isotopy to be rel boundary. So you've got some isotopy of the interior only, and the boundaries is fixed, but you're always passing through surface braids.
Maybe Kamada's equivalent does not is equivalence.
Kamada's
fiber preserving.
Oh yeah, fiber preserving. So you want you want to sort of somehow preserve the interaction of the branch points so they don't merge and stuff.
And in this case, it's an open problem.
Yeah, so this is something I was kind of sweeping under the rug, because there's a question of like Markov's theorem essentially says, like Kamada's Markov's theorem says that you're isotoping through braided surface or through surface braids. But it's quite possible, like if you start with a simple surface braid and end with a simple surface braid, you might have to pass through higher degree branch points. And so that is an open problem as to whether that can be done through simple surface braids. So yeah, so there is a fiber preserving condition, ambiently isotopic, fiber preserving ambient isotopy. Yeah, that's Kamada's definition. Yeah. So this is so I've drawn these pictures in terms of banded unlinked diagrams, which are sort of implicitly give you simple surface braids. But to sort of combine the braid chart technology with the Markov theorem, you would need to know somehow that you're only passing through simple surface braids, which is an open problem. So I kind of feel like there should be a way to prove it by like, if it is true, I feel like there should be a way to prove it by like applying the band moves in some like braided way, but I don't know. I've thought about it a little bit and I don't think, yeah, it's nothing obvious, so. Yeah. Oh. Okay, so simple surface braid, I mentioned it a little bit earlier, but I don't know that I wrote it down. It's a surface braid where you only have degree 2 branching. So you only have branch points that look like this. You don't have any of these like branch points that like where you have like this higher, I You know I can't show pictures right now, but you don't have any like degree 3 branchings or degree 4 higher. You only have degree 2, and then, yeah. So at some point, I think in the talk, I said everything I say about from now on will be about simple surface braids, and so most of what I said today was just about simple surface braids, but there are some subtleties for sure. Okay, all right, thank you. You're waiting. Okay. Yeah.